Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 5 of a 7-part mini-series within that larger playlist. Here we're looking at balanced two-factor factorial design without interaction, and we're going to look at the F-test for factor effects. As a reminder, the model is y equals x star beta star plus epsilon, so it is a linear model. And then the design matrix can be broken up into the grand mean, the x alpha for the factor A and x beta for factor B. Epsilon is normally distributed, mean vector 0, covariance matrix sigma squared I. Now the treatment A, the test for no treatment A effect is this. The null hypothesis is that the alpha vector, so all the parameters in the model must be a constant vector versus they're not. And I'll explain that in a second. So the test statistic is the sum of squares for treatment A divided by its degrees of freedom, which we derived in previous videos in this mini-series, divided by the sum of squared error divided by its degrees of freedom. And these sum squares are independent, which we did in part 4. We proved they were. So it creates a non-central F distribution with A minus 1 degrees of freedom here, and this non-centrality parameter, which we also derived in the previous video. Now, under the null hypothesis that each component or each alpha parameter is constant, then makes this be 0. Then it becomes a central. So under the null, the test statistic follows a central distribution. Now, if they're not constant, then this is a positive number, right? Because they're summing up squared things. Then the non-central F distribution is shifted to the right, which makes it more likely to be in the rejection region. Anyway, so that's treatment A. So treatment B effect, the test for it, is that the beta vector is a constant vector versus it's not a constant vector. The test statistic is the sum of squares for treatment B divided by its degrees of freedom, divided by the mean squared error, which is the same as this right here. And that is a non-central F distribution with non-centrality parameter this. So if under the null hypothesis that the beta vector is a constant vector, all these are the same value, which means they equal the mean. So this is 0. So under the null, the test statistic follows a central F distribution. Now the Anova table for this design, balanced two-factor factorial design without interaction, we have the source factor A, factor B, sum of squared error, and total. And then you could write these in scalar form, and we derived those in previous videos, but it's so much easier to write it in matrix form using the quadratic representation of it. The degrees of freedom associated with those sums of squares is actually the rank of that matrix in the middle. Now, often people have rules of thumb, how many parameters we're estimating, how many restrictions, and those are good rules of thumb. But in reality, it's the rank of that quadratic matrix is what the degrees of freedom is. Now, the mean squared error is the sum of squares divided by its degrees of freedom in each case. And then the F test statistic is the mean square divided by the mean squared error. That's what this is. And the same way for this. Now, notice that in this test, we didn't talk about type 1, type 2, type 3, etc. And that's because it's balanced without interaction. And in that case, so note, since the design is balanced without interaction, those type 1, 2, and 3 sums of squares are equal. Now, I'm going to point you back to a video or a playlist I called Regression Approach to Anova, where we looked at that and showed that to be true. Now, I want to show you that it is true in this setting. I'm going to do a partial F test, which says you fit a full model and then a reduced model, and you look at the difference of the sum of squared errors, and I'm going to show you that it's equal to one of those tests that we just looked at. So here we're going to assume that the alpha parameters are 0 or not. Remember, these are mean vectors, so they're all 0, or they're not all 0, right? Not equal to. So the full model, of course, is this. And so sum of squared error is, I minus m, I minus m. That's how I kind of remember it myself in a sort of a weird way, I guess. But so this is the sum of squared error for the full model. M is the perpendicular projection matrix onto the full column space. Here, the reduced model, we take out alpha, and then we find the sum of squared error associated with it, which is I minus m, but this m is the perpendicular projection matrix onto this reduced column space, which is m beta. So now the partial F test is the difference of those sum of squared errors divided by the degrees of freedom associated with it, which is actually the rank of m minus m beta. And I have a playlist in the linear regression setting that we really go into great detail about these partial F tests. And this divided by the mean squared error for the full model. Now here, this is the quadratic form for this, and this is the quadratic form. Now, if we left factor out of y, which is this one, and we right factor out of y, which is this, we're left over with this. Now, the i's cancel, right? Minus, that's a plus. But m in this setting is m alpha plus m beta minus j. So the m betas cancel, and we're only left with m alpha minus j. And so this is the mean square for treatment A. So this is sum of squares for factor A divided by its degrees for freedom, which is mean square A, for treatment A, divided by the mean squared error. And that's exactly the same test that we looked at for the test statistic on page 1. So they are equal, and that's why we don't really talk about the different types of sum of squares in balanced designs without interaction. Well, that's all I have for this video. Hopefully you enjoyed that. The next video will be on contrast, if I'm not mistaken. Hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.